Okay, well, welcome everybody. We'll go ahead and get started with our seminar today. So my name is Tyler Dick, and welcome to the virtual William W. Hay Railroad Engineering Seminar. Before I introduce our speaker, I would like to remind all of our listeners that you can ask questions using the question box on the side of your screen, and one of the moderators of the seminar will read them to the speaker at an appropriate time. Typically, we'll hold those for the end of the presentation. The William W. Hay Railroad Engineering Seminar Series is sponsored by the Rail Transportation and Engineering Center here at the University of Illinois Urbana-Champaign. On behalf of all of us, we thank the Association of American Railroads, BNSF, CN, Hanson Professional Services, and Union Pacific for their ongoing support of RailTech. It is greatly appreciated by those of us here on campus, as well as those participating by the internet. I'd like to also extend a welcome to the over 150 people who registered for this seminar from at least different 8 countries around the world. This includes representatives from freight and passenger railroads, transit organizations, federal and state DOTs, engineering firms, universities, research organizations, technology developers, and suppliers, among others. We are very pleased that you can join us for what I know will be a very interesting presentation. For those of you who wish to receive PDHs for your participation, please send us an email at the hayseminar@illinois.edu email address that was in the email invite, and follow the information described in the email announcement for this seminar. This is our second Hay Seminar series, or Hay Seminar of the spring semester, and we have several more already scheduled, so please check out the RailTech website for further details on our future seminars coming up for future weeks this spring. Okay, today's seminar is going to introduce a very important topic, and a major factor in railroad operational efficiency and punctuality is the quality of the train planning and dispatching. The work presented today proposes a methodological tool set called the dispatch analysis problem that can analyze recent empirical train dispatching data against an optimal dispatching plan. A multitude of questions can be answered using this approach, such as the effect of dispatching actions on the optimality of future planning, corrective actions to mitigate the negative impacts of past dispatching errors, and identifying trains that introduce secondary effects to other train plans. This presentation will demonstrate the application of these dispatch analysis methods using illustrative case studies from a North American freight railroad. Our speaker today is Dr. William Barbour, who is a research scientist at the Institute for Software Integrated Systems at Vanderbilt University, and he has a focus on researching transportation cyber-physical systems. Dr. Barbour earned his PhD in civil engineering from Vanderbilt University, his master's degree in civil engineering from the University of Illinois, right here in Urbana-Champaign, and a bachelor's of science in biosystems engineering from the University of Tennessee, Knoxville, and has previous work experience with Oak Ridge National Laboratory and CSX Transportation. Dr. Barbour's career and research interests focus on the application of novel and advanced computational techniques to transportation systems engineering, including the freight rail transportation domain through ongoing industry collaboration with Class I railroads. I've had the pleasure to collaborate with Will on several research projects, so I'm very pleased to introduce Dr. William Barbour to present his seminar today, entitled Rail Dispatch Analysis Methods Using Optimization and Empirical Data. So Will, we'll turn it over to you.
Thank you, Tyler, for that very good introduction. I very fondly look back on my times attending Hay seminars in person at UIUC, and I promise it was not just for the pizza, which I must remark was the absolute best on campus. But these seminars truly are a really interesting exposure to a variety of topics around the rail domain, and it's a pleasure and an honor to present at one after having seen them all these years. So as Tyler mentioned, I'm going to be presenting on dispatch analysis methods today, and we're going to look at those in the context of optimization and empirical data. This is a very fruitful area of research across the world and across many different types of railroads. And today we're going to dig in very deeply to some very detailed rail dispatch scenarios and how those can affect efficiency across the railroad. So Tyler very nicely summarized my personal background. And I will note that I'm a research scientist at Vanderbilt University now, and the cyber physical systems that we study across transportation domains are really confluence of physical infrastructure systems and the cyber components that we can supplement those with, which include data-driven methods, artificial intelligence, and optimization. And one of the things that intrigues me about the rail domain is that it was sort of one of the pioneering cyber physical systems. The history of the integration of technology into railroads dates back many decades, and many of these technologies that were developed for the railroads are still in use there and in other domains. So that includes everything from signaling systems and centralized traffic control to now the very complex optimization and computerized dispatching and planning systems that we have. Very interestingly, when I present on this research to computer scientists, they get a kick out of the idea that a very common term in computer science and synchronous programming is the semaphore, which is used in threading and multiprocessing, and then that semaphore dates back to the railroads and traffic control devices on roadways. So you can see all the way to today the influence of some of these technologies. And looking more at what the railroads are dealing with today, there's sort of an emerging area of competition amongst between railroads and emerging autonomous driving technologies that will be deployed on the roadway now and in the coming years. These autonomous freight trucks are going to be hitting our roadways and significantly disrupting the current economics of freight transportation in the United States and in the world. This is certainly not to say that things are lost when it comes to the railroads. They play a vital role in our transportation system today and will continue to do so. But in order to stay as competitive as they are today, some degree of innovation will be required. And one of those innovations is coming in sort of the digital transformation of the freight rail domain. As I mentioned, there's a long history of this, but it certainly looks very different today. And autonomous trains are certainly a component of this, but there are many technologies that can supplement what we're doing today on the railroads and get us part of the way there without exactly going the full extent and taking the driver out of the train. So again, the future is still looking bright for freight rail for a variety of reasons, but this digital transformation will certainly play a role in its continued future. So at the heart of the freight transportation landscape is the fact that railroads have an enormous efficiency advantage, but at the same time, they're extremely costly in terms of infrastructure. So a large investment is needed up front, but for that investment, you get numerous efficiency advantages. But there are still particular challenges that the railroads have to overcome, such as terminals and junction points. This is a map of just the Nashville area. This is a vital junction point for railroads around the Southeast. And just in coming into Nashville, we have 5 different lines headed out to major cities around the region. So this point requires enormous coordination, and this is sort of one of those choke points that can really dictate how well the railroad can function. An additional challenge is that traffic is very heterogeneous. Compared to the sort of performance variability of trucks out on the roadway, we see much wider performance heterogeneity amongst trains in terms of the power that they're carrying, the length of the train, its tonnage and ability to go up and down inclines, and its cargo and priority. So this is a management challenge for sure. And then sort of at the end of all this is the fact that railroads are highly scheduled and highly interdependent in terms of their operations. So any delays that happen to that schedule, if they can't be absorbed, must be accounted for by shifting that schedule continuously. And those those delays are sort of inevitable, and the triggers that from which they often result are in many ways unavoidable. And this can be everything down to weather. As we've seen recently, I'm sure I don't want to know all the complexity that the freight railroads in the southern United States have had to deal with recently. And this extends to their interactions with other railroads, their interactions with customers, and then just, of course, the random unforeseen mechanical issues that occur during normal operation. And the result is that even these small delays can harm the ability to run the railroad to the original schedule or the original plan. It can harm our ability to plan into the future because of lack of precision. This consistency is something that is a continual area of improvement. But again, some of these things, some of these delays are just unavoidable. And so this is a major motivating factor for this research. This research that I'm presenting today is sort of one component of my larger dissertation, which was done on broadly sort of data-driven tools for freight railroads that help with operational improvements. And so that's sort of been the overarching research question during my time researching the freight rail industry. And I think it's a very important one, considering the landscape of things today and where the future is going. So let me give you an example of sort of what a data-driven railroad workflow looks like. Railroads are intensely data-heavy industries. They are today collecting data streams from almost every single asset out there on the roadway, or sorry, out there on the railroad, as well as many external data streams. They're ingesting weather data from other railroads, neighboring points, and data from customers continuously. And these are just some of those sources. Many of those data streams are used in real-time operational systems. Because the railroad is extremely dynamic, things like routing, scheduling, and asset allocation have to be continually adjusted in real time. Some of my previous work that is also included in my dissertation, but we won't discuss today, has been on Eta prediction for particularly variable segments of the rail network, looking at the use of machine learning and historical data to predict ETAs more accurately for trains. And then in addition to real-time operational systems, the vast majority of this data is archived historically. And that's important because it can be used to train models and extract statistics about how the railroad operated in the past, so that we can make a better expectation of how it will perform in the future. Importantly, for that historical archive of data, as anybody who's worked with large amounts of data can tell you, data cleaning is an essential part of a data-driven system or a data-driven modeling. Data cleaning is certainly not the most glamorous part of this process, and certainly not the most fun, but it's essential nonetheless. And then you can see that this sort of feeds into the primary focus of today's talk, which are these dispatch analysis methods that I've developed over the past couple of years, which we'll talk about at length today. And importantly, all these systems are sort of ingested and interpreted by information consumers. The railroad is very reliant on computers, but overall it's humans that are making the decisions, whether that's at a very detailed operational level or at the tactical or strategic level. So I want to take a brief moment to go through really quickly a little bit about this data cleaning process. Not just because data cleaning takes a while and we spend a lot of our time here over the course of research, but because this sort of feeds logically into some of the dispatch analysis work that we'll talk about for the rest of the time. We've developed some methods here in the data cleaning area that we call automatic data reconciliation. The reason for the fancy title here is that these methods that we've developed automatically fix erroneous or missing rail dispatch data, and importantly, they guarantee the feasibility of the resultant train trajectories. So this isn't necessarily the normal sort of denoising or outlier detection that we're used to in data cleaning, but it includes details all the way down to the interaction between specific trains. And so because of that, we use as the backbone here an optimization-based dispatching model. So this is sort of the same model that railroads use internally for planning activities, where we might try to get all trains to their destination as quickly as possible, which is an optimization problem. But importantly, it obeys the rules of the railroad and the physics of not running trains into each other. So again, the research problem here is to perform this data cleaning automatically on very large scale data sets. This involves fixing errors and fixing missing points. And ultimately, we want to guarantee the feasibility of this dispatch data. So for data sets of millions of points spanning an entire rail network and or many years of data availability, manual data cleaning, even with an army of data cleaners, is a pretty infeasible process. So hence the need to do this automatically. So as I'm sure pretty much everybody is aware, these dispatch decisions and the dispatch data all sort of come down to the interactions between trains. We of course have the ability for trains to overtake each other, and this is, as I should note, this is sort of assuming we're on single track territory. This is where most of the methods that I've worked on are centered, but this is directly extensible to double track territory or larger. But certainly in the single track context, we have overtakes of trains as well as very frequent meet events of trains where trains in the opposite direction pass each other. And that diagram was sort of what it looks like out on the track. But we will frequently look at what this looks like in terms of a string line diagram. So this is just a space-time diagram that shows the track topology on the y-axis. So in this case, we have two single tracks and one siding where trains in the opposite direction or same direction can pass each other. So in this case, I show one track sort of heading north to south on this diagram, and that occurs over a period of time. And then we may have trajectory points for another train, which clearly meets that train going in the opposite direction. But we do in some data sets see frequent missing data points, be that because of a sensor error or some miscoding of the data, or just a random bug in the code that translates that into a database. But these missing points can sometimes be interpolated and sometimes just be missing entirely. And in this case, for this diagram, we see very clearly that this is a set of infeasible trajectories. These the intersection point implies that these trains passed on the siding track, when in fact we know that this must have occurred on the siding track. So the data reconciliation process is tasked with finding the correction to this data that satisfies feasibility between these two train trajectories. So, and I'll wrap up this discussion of data reconciliation with saying that this method performs much better than alternative methods that we might use, such as interpolation of these points or sort of ad hoc rules to correct them based on sort of just methodically going through them logically. And we applied this on a data set of 75 million timing points. We found a very low error rate, but Errors can be introduced for a variety of reasons, and tracking down those errors and their sources is not always an easy task. But this method performs that task extremely quickly, and can give us a very clean data set at the end result, and also help us to fix some of those errors upstream. And this is sort of an example of one of these complex train interactions that is extremely easy for data reconciliation to find and correct automatically, but might not be super apparent to a human going through this data manually. So coming off that brief detour of data reconciliation, I want to move on to dispatch analysis, and you'll see very quickly how these two problems are related in the optimization sense. But this dispatch analysis methodology, we use it to analyze train performance and dispatching performance relative to a schedule or an optimal plan. So as I stated earlier, railroads are extremely scheduled networks and systems, but those initial schedules don't always work out to plan, and that'll have to be adjusted. So we want to look at how the train performance and the dispatching actually worked relative to an initial schedule or initial optimal plan. And we can use these methods to look at both historical data, and they could also be adapted to look at real-time data as the network is evolving, though we don't show that we don't implement that specifically in this work. We use a sort of simulated historical data stream. So briefly, our research problem here is to determine the actions of trains or the dispatch actions that negatively impacted the ability of the railroad to run to an initial schedule or plan. Those initial schedules or plans are almost always generated, but they frequently have to be changed in real time based on sort of deviations from that plan or changes to the network state that necessitate a change. And the hopeful result of this is that we can isolate specific events, specific periods of time, or even specific trains that are problematic to the original schedule, and we can help attribute the sources of delays and deviations, and use all of this knowledge to inform future plans, inform operating strategies, or even give dispatchers feedback on how they're doing. So in my sort of current research area and in our domain and terminology, we refer to this overall process of taking a plan, running the system forward in time, and then regenerating a plan as a model predictive control framework. This is implemented in many different domains. Everything from, of course, planning and executing a railroad to autonomous vehicles and many other areas. And specifically in the railroad context, this is often referred to as the replanning problem. So identifying deviations from the original plan, developing a new plan, and executing that. There has been a very large amount of research done on optimal replanning and replanning a complex problem very quickly using heuristics. But all these problems come back to the sort of core optimization of dispatching trains as effectively as possible. So some of the questions that we'll look at as they relate to the replanning problem are how does the cost of the new plan increase or evolve over time, and which deviations are causing that increase or narrowing down those costly plan increases to specific periods of time. And ultimately, this information can be used to attribute causes for causes for those increases in cost. So to give a brief illustrative example of why not every scheduled deviation is created equal, we'll take again a very simplified string line of two trains traversing a single track network and planning to meet and pass each other on middle siding. Here's the original dispatch plan, and if we encounter a scenario where train 2 is delayed a significant amount, we are able to replan in real time to make that meet event happen at the northern siding as opposed to the middle one, and incur actually a runtime decrease for train 1 and incur sort of very little additional runtime increase for train 2. That's sort of a minimal impact to the schedule. Let's take an alternative case where we have sort of these two trains again in opposing directions, but in this case we have two very long trains that can't meet at a shorter siding, or we could have that siding unavailable for a variety of reasons. But in this case, where we constrain this meet event to happen at the northern siding, we can see that a similar delay, this time in train 1, will actually cause a secondary effect or a knock-on effect to train 2, causing it to delay significantly more as well. So this is a sort of classical example of that interdependence between trains and how one small deviation from the schedule can have a ripple effect to other trains and other portions of the network. So the three specific questions that we're going to look at with the dispatch analysis methodology, they all sort of get at this overarching research question that I identified earlier, but we'll break them down specifically to these three. Question 1 being, what is the overall dispatching cost in terms of sort of the current cost and future, given the current network state? And I'll explain more about exactly what that means in a little while. We'll also look at how the network state could have been altered to improve replanning options into the future. So this is sort of a hypothetical question about what could have been done differently in the past. And we'll also look at which trains have the largest impact on the ability of the network to run to its original schedule. So I'm going to get into a little bit of math throughout explaining this dispatch methodology. The math is not intended to be particularly scary or anything, but it does sort of illustrate these questions in optimization terms. And if you're familiar with the optimal dispatch problem, which I'll explain briefly, you can see how this methodology, the dispatch analysis methodology, is able to be adapted from this core optimal dispatching problem fairly easily, and so it would not be burdensome given this optimal dispatch problem available as an existing railroad tool. So the optimal dispatch problem, in very broad terms, is a minimization. Which, therein lies its optimization problem. A minimization of, let's say, total train runtime or an equivalent measure that we're trying to minimize, and we subject this minimization problem to a variety of constraints that dictate how the railroad must operate. Some of these are, of course, physical, as in trains must meet and overtake each other in physically feasible manners, and some of these could be railroad specific as well. And when we put this in mathematical terms, we are minimizing some function. In this case, of course, we use f, and f is just a function of our continuous variables and integer or binary variables, which describe train movements. So we're minimizing that function f, and we subject that to some linear algebra here, which is sort of just the standard notation for identifying constraints. We will put the constraints in a much easier form to understand, but this is sort of how the optimization solver sees them, as three matrices. So I'll give an example here in mathematical terms, but I promise it's quite easy to understand. This will be an example constraint, and you'll see how this could be fairly easily replicated to describe sort of all train movements and the rules therein. So in this case, we see a diagram again of a single track network territory. In this case, we have 5 track segments, index 0 through 4, and some of these are single track segments and others have sidings. We have 2 trains, in this case, train I and train J, heading in opposite directions. And as you saw in the optimization math earlier, we have continuous variables described by X, and those variables simply just describe the time at which a train, which is included as one of the indices, in this case, a train I, reaches the end of track 1. So therein lie the two indices of that variable X, and likewise, the variable xi2 describes the time at which train I finished traversing track 2. We can introduce another variable at the points where tracks diverge, in this case sigma, and sigma I1 indicating which of these 2 tracks, either the main line or the siding track, that train I took as it traversed the network. And these variables can then be combined to give us one of the constraints that will feed into our optimal dispatch problem. And in this case, we condition this on sigma I being 0. So that's saying that train I took the mainline track segment. So if that is 0, then we will subject the timing points of train I such that the traversal time of train I over a track segment is no more than t minutes. So this is just a way of encoding those or the free run travel time of the train and the timing points of the train across that track. And likewise, we can look at the alternative case, the converse of that, where the train I did indeed take that siding indicated by S, and in that case we just subject that train's timing points to a different minimum travel time, in this case denoted by U. So these are just 2 of the many constraints that go into this problem. They're sort of written here as logical constraints. In actuality, they have to be formulated as mixed integer constraints, such that they can feed into that into the broader optimization problem. But these are these are the logical building blocks from which we compose the optimal dispatch problem. There are, as I mentioned earlier, a variety of additional constraints, and this just gives us, at the end, a fairly large optimization problem with, for a fairly modest amount of time, gives us around 6,000 variables and 16,000 constraints. That certainly sounds like a lot, but is well within the capabilities of modern optimization solvers. So this problem is complex, but it is certainly very solvable, and these optimization tools are ones that the railroad I would assume most freight railroad or all freight railroads have readily available to them for scheduling, planning, and dispatching purposes. So you will see from this problem that we introduce some clever modifications to the optimal dispatch problem, but it's very important that we sort of understand the fundamentals there. Very briefly, our case study data set is a couple years of dispatching data from the Essendon North CSX subdivision between Nashville, Tennessee and Birmingham, Alabama. This is single track territory where we have 17 sidings between those 2 cities across approximately 190 miles. This is a high volume track segment with 15 to 25 trains per day. And its free run traversal time is quite modest, 4 hours. If that lower bound traversal time is rarely realized because of the complexity of operations on this section, but it certainly is possible. So from that historical data, we mine that to discover sort of the constant values that we introduce into the optimization problem, things that we just saw, such as mainline segment times and siding segment times, and then some other parameters such as meet headway time and train follow headway time. So that's all mined historically, but of course we could also introduce those sort of by railroad rules or analytically computed from track length and speeds. So getting back to the three core questions that we outlined for this dispatch analysis methodology, let's take again question 1. So this is what is the overall dispatch cost given the current network state? And so the overall cost we break down to the current and the future cost. So specifically, this is asking up to a certain point, which we will denote tau, at a certain time. We will fix the network state up to that time and then replan from that current network state out into the future to the conclusion of the dispatch problem. And this replanning is the best possible future performance given the current network state and the future out past time tau. And why that is important is because this is sort of, again, how the railroad is operated. So that continuous replanning process allows us to continually try and realize the best possible future performance. So let me explain this graphically. Again, we sort of begin the schedule or the dispatch scenario or the day, as it were, with an optimal or a baseline plan or schedule for how the trains will operate. We can at any point, in this case I used tau equals 300, so approximately sort of 5 hours after the day has begun, we can look at how the trains are doing empirically compared to the original schedule or the optimal plan. And we can see the empirical string lines are shown in blue, the optimal plan in green. We can see that many of the trains here have diverged from their optimal plan, some a significant amount and some a fairly modest amount. But because of that new network state, of course, we are required to replan because the original sort of continuation of the optimal plan would no longer be feasible based on where the trains are currently. And so this is what that replanning would look like sort of going forward from this point, tau equals 300. And so we can look at this replanning process, not just for one point in time, but we can look at this as it evolves across a full time period. So taking the extremes first, at tau equals 0, so the network has not evolved at all. We're still sort of in our initial network state, and the baseline optimal plan is still perfectly feasible. It may be difficult to run, but assuming we have all the constraints right and everything, the optimal plan is possible. And then when we've evolved the network to the end of the dispatching time window, in this case we use tau equals 600, 10 hours into the future. At that point, basically there is no replanning left to do. The network has fully evolved to the time that we're considering, and no amount of replanning is possible or necessary after that point. And so those 2 points are shown here on the on this graph here as the baseline, the optimal plan cost. So if the network could run perfectly to optimality, what that cost would be. And then here as the upper bound, this is sort of the tau equals 600 cost. At the very end of the day, after the network is fully evolved, what was the empirical cost for this dispatching scenario as we saw it actually happen? And our question really is, how do we get from the beginning of the day to the end of the day? And at what points across the day did we accumulate the empirical costs that we ultimately realized. And so we go through this iteratively and sort of evaluate this problem at each time tau between those 2 points, assuming that we fix the network state up to that point and then optimally replan into the future. In this case, for this example, we get this curve here, and I'll explain a single point on here sort of graphically. This is, as I showed earlier, that string line for tau equals 300. This is what that point looks like on this plot. And the way we interpret that is at this point, the combination of, or the sum of the cost, the dispatching costs that we've realized empirically thus far up to this point, plus the cost of the plan going forward after optimal replanning is this point here on the graph. And the way we interpret additional points on here are that we're really looking for the cases in which we saw this jump between time periods. So this graph just shows the for increments of 30 minutes, how much that replanning cost increased, and we can look at important time periods during this dispatching scenario in which we incurred a very large additional cost. So you will actually see this. I'll show the entire replanning process here in an animation just in a second. But just to very quickly walk through a little bit of the math here, this is essentially the dispatch optimization problem, except we add an additional constraint into the mix here, which is that we fix all of the timing data to its empirical values up to time tau. In this case, we denote that tau minus. So all those points up to time tau, we just set the difference between the optimization variables and the empirical values equal to 0. And by solving the remainder of the problem after time tau, this is sort of the optimal replanning problem. So looking at this situation graphically, if you recall, there was a very large jump in the replanning cost that occurred between 390 and 420 minutes. And there are other significant time periods throughout here as well. But I will go ahead and start stepping through here and evolve this, the network state. And you can see that relative to the optimal plan or the baseline plan, which is shown in red, thus far trains are more or less obeying that optimal plan. But then we do start to incur some delays, and the first delay seen here doesn't sort of register for a while, but a train is delayed for a very long period of time on the first siding that it comes to, and quickly adds additional replanning costs to the problem. I will evolve this a little bit further, and you'll see that train performance is matching the optimal plan fairly well. And then we'll come to another period in time in which the progression of trains during this time period adds significant replanning cost into the future. And we see that as we evolve this towards the end, this schedule stretches out significantly further beyond what was theoretically possible earlier on. So this shows us sort of the situation relative to optimality. But of course, this doesn't capture many of the nuances that actually occur out on the railroad. Dispatchers may have a variety of reasons for which they choose the actions they do, and some of those may not be captured fully in this problem. But it certainly allows us to isolate a period in time during which that replanning cost jumps significantly, and really the network state hinders our ability to replan well into the future. So I just composed a few of these dispatch periods during a month of operations onto this single graph, and you can see that this that certainly the patterns under which the replanning cost is distributed can vary quite widely. I highlighted 2 different mornings from 2 different days here in purple, and you can see that one of those incurred a lot of its replanning costs sort of in the middle of that dispatch window versus the other that incurred a lot of that cost earlier on. So that certainly identifies 2 very strategic periods during which we should look more closely at the dispatching process and how the network evolved that really led to that replanning being compromised. So I'll move now on to question 2, which is, if you recall, a little bit of a hypothetical question about how the network state could have been altered to actually improve replanning options. So this is sort of a logical extension of question 1 to the point where we're asking, are there very specific examples where we could have changed things and put ourselves in a better situation? So in the interest of time, I won't go through too much of the math in huge detail, but our objective here is to take that replanning cost at a time tau. Again, we're recycling that timing value, and we're going to call that replanning cost. Again, from the previous problem, you'll recognize this graph. If we take this replanning cost at a given time and ask to reduce that replanning cost to a hypothetical amount, which we'll call R prime, what would we have had to do to the network state in order to make replanning possible down to this specific value? So we're going to make network state alterations that sort of occur before our analysis point in time, tau, and those network state alterations, because we changed things in the past, that will change our ability to plan things into the future, and will hopefully improve on our ability to replan and get trains to their destinations faster. Again, I'll go through the math really quickly here, and just note that in this case, for this problem, the objective function actually changes here to the point where we're trying to minimize the changes to timing points before time tau. Again, minimizing those changes, trying to find the smallest ones as possible in order to achieve a reduction in the total replanning cost. So I can go through more of this or go through more detail on this if people are curious at the end. But very importantly here, you'll see the normal dispatch problem constraints. So this is sort of just a modification of the objective function and the addition of one small constraint. Yeah, so I'll explain this graph fairly quickly so that we can sort of get to what this looks like in terms of a string line diagram. But of course, we have this replanning cost at time tau. We've sort of inverted the axes here, but we're trying to get back down closer to the baseline plan cost. So modifying the network state again to reduce that dispatching cost. And we're really looking for small changes in the network state that have a large impact on cost. And in this diagram, we see that we can reduce cost from this point sort of out here near 3,200 down to around 3,000 total minutes of train runtime with a relatively small alteration to the network state. So just based on the fact that this is significantly under this sort of one-to-one line, we're getting a very good return on our investment by modifying the network state. So in this particular case, we can reduce the replanning runtime by over 3 hours by making a 45-minute adjustment to the network state. And what that looks like based from some empirical data, a very large portion of that is made up by this small change here. The initial replanning after time tau, sort of what we're going to have to do from this point going forward, would have been this red string line. But by changing these timing points from their empirical values, the blue trajectory, to the points on this green trajectory, we're able to realize a better overall trajectory for this particular train to the tune of 25 minutes. So by adjusting these earlier timing points, this train could have run 25 minutes faster, and we would have gotten a significant runtime reduction out of it. So this is, again, just highlighting these really impactful small changes that would have had an outsized ability on our replanning into the future. And this is just one such example. And now I'll spend a little bit more time on question 3, because this one I think is the results are particularly interesting. But we're now asking the question, which trains have the largest impact on the ability to run to schedule? And to solve this problem, the question might make a little bit more sense once I sort of walk through the process, but we will fix the trajectory of one train, which will denote W, to its empirical values, so to what it actually ran historically, and we will essentially run the optimal dispatch problem around that one train. So when we fix its trajectory to what it actually ran, how does that impact the optimal planning for all of the other trains versus their baseline optimal values when we didn't fix train W to a specific trajectory? And so going back to this very simplified example, in this case, the initial plan had a total planned runtime of, let's say, 120 minutes. And when we fix the trajectory of train 1 in this case, how does that affect the trajectories of the other trains? And if this is the ultimate outcome, then we have a total replanned runtime once we fix train 1 of 210 minutes. And so we can break that down into what we call the primary effect, which is the added runtime of the particular train we're analyzing, and the secondary effect, which is the knock-on effect to another train on the network or all other trains on the network. And in this case, the primary effect was 40 minutes, and the secondary effect was 50 minutes for a total of 90 additional minutes of runtime in excess of the optimal plan. Again, looking at the math, and I promise this is the last math slide that you'll have to deal with today, we are, in this case, minimizing the total runtime of trains as our objective function. And we're subjecting that to the normal dispatch constraints, again, summarized by this linear algebra here. And then we're adding an additional constraint, which fixes the trajectory of train W to its empirical values by basically saying the difference between those two trajectories is 0. And so here is an example of the result of this process, iterating across each train within a dispatch window. We fix each train's trajectory and then replan around that fixed trajectory, and then break that result down into the primary added runtime from fixing that train's trajectory, and the secondary added runtime, that is the effect caused on all the other trains as we try to replan around the train's trajectory. So importantly, either effect, the primary or the secondary, can be negative, but the net effect must be that runtime increases or at the very least stays the same compared to the baseline optimal plan, because for an optimization problem, introducing additional constraints can serve only to increase the value of the objective function. But let's take a couple examples of trains that we see in these results. The first is train E07 here. Compared to its original plan, train E07 experiences a large increase in primary added runtime. Excuse me. So when we fix its trajectory compared to its optimal baseline, that added runtime that it actually experienced is well over 200 minutes. But its added runtime in the secondary sense is quite minimal. It really didn't have much impact on other trains. Taking the other extreme here, train R59 had a very small amount of primary added runtime, that purple bar, to the tune of about 10 minutes. But the secondary effect that fixing its trajectory had on other trains was quite large, closer to 100 minutes. So this train had somewhere on the order of a 10-to-1 effect in terms of primary versus secondary effect. And interestingly, you sort of see this negative effect that I mentioned here, where in fact allowing train G21's original trajectory or original runtime to increase actually allows other trains to decrease their runtime. But of course, the net effect here is still positive. So let's take this train R59 because it is clearly an important one where a small increase to its runtime had a very large effect on others. So this is the original optimal plan for the trains in question. You see R59 here. And then let's look at what it did empirically. So again, its added runtime compared to its optimal plan was only an additional 11 minutes. But we know that it had a very large effect on other trains. And here is the secondary effect that caused. So replanning, basically with this blue trajectory substituted for R59's original optimal trajectory. And the effect that has is that train Q11 here is required to deviate and hold at a siding such that these two trains coming in the opposite direction may clear before train Q11 is allowed to finish its route. And this is because train R59, by delaying only 11 minutes here, just closed this window before the other two trains needed to get by. So this is a snapshot of the overall dispatching picture, but it shows you that that very large secondary effect that just 11 minutes can have in terms of adding an additional 83. I compiled these results across the other trains in the same month as that one example, and then this is sort of the scatter plot of primary added runtime versus secondary added runtime. The trend line here is showed by this dotted line, and the trains of importance here are the ones that lie significantly above this trend line, meaning that their primary added runtime had an outsized effect on other trains' ability to run their optimal plan. Taking these ratio values, primary versus secondary ratio, as a histogram, we can then identify very easily those trains that had an outsized effect on others because of fixing their trajectory. So I will conclude the talk now just by mentioning again the data reconciliation process that I talked about very briefly. And hopefully you see now that that it is related to the optimal dispatching problem and the dispatch analysis methods, in that it uses this sort of same core set of constraints that are required to develop a plan for a railroad, and it reformulates the objective function for that optimization problem, and gives us back out on the other side a data set free of infeasibilities and missing points, which is very important in systems such as dispatch analysis, which rely on clean data coming in, clean dispatch data. And that dispatch analysis methodology is able to reveal those time periods, the events, and the specific trains that were critical to dispatch quality. We can then use the results of this to look further at improvements that could have been made, or things that could have been re-strategized to result in a better outcome overall. Again, I sort of, what we're looking at is a relatively simplified picture of how the railroad actually works. we're seeing only train movements, but as you know, there are many other factors to consider that sort of we can't see just based on train movements alone. So in many cases, those could be having effects on why decisions were made, but highlighting these areas that are questionable as sort of the first step to narrowing down to the ones where dispatching did not work as well as possible, or train performance did not match what was really possible in theory. So that is the conclusion of the talk today, and I would be happy to take any questions on anything that we covered.
Well, thank you, Will, for an excellent talk and a fascinating topic, and to a lot of attendees here. We've had some great questions roll in, some great graphics in the presentation as well. Before I get to the questions, just one comment I had is in addition to some of the business implications or uses of your model, could you envision this as something that could be used to potentially train or educate dispatchers on the consequences of their decisions, and sort of training or either a human dispatch or even a sort of a computer artificial intelligence dispatcher system to make better decisions?
Absolutely, yeah. There are there are a variety of applications in which this is, everything from moderately useful to a very critical system. Dispatchers, I'd certainly don't mean any of this to take anything away from the complexity of the job they do and the multitude of factors that they consider at any one time. That job is very, very difficult. I've never done it personally, but I've spent a lot of time talking to dispatchers and understanding how the process works. It's not simple, and everything moves surprisingly quickly. Helping give them decision-making tools is certainly an area where computers can supplement the tasks that they are already doing. And there are computer-aided dispatching tools already in deployments in many situations, but sort of looking at continuing to look at things relative to an optimal or theoretical plan as the railroad evolves. This can really help us, as you were saying, sort of look back at what could have been done differently, so it can be used in the real time and the historical sort of learning lessons context.
Okay, so moving on to some of our questions online, we've got a esteemed group of question answers here, some real big names here, so you've got a great audience here. One question is, positive train control systems, now have GPS receivers on locomotive that are having a lot more train position data. So just a question of, how would supplementing your essentially your control point data from the dispatching system and improve your analysis, and are railroads using that data to support this type of analysis and procedures?
Yeah, that's an excellent question, and positive train control is going to add a whole new dimension to these data-driven methods, this one included. The ability to know a train's current location down to the GPS point gives us just a large amount of additional visibility beyond the sort of discretized, timing point string line diagrams that I was showing. So if we know the train's current position to a higher fidelity, all trains on the network, then we can compose a higher fidelity string line diagram. And the dynamics engines that underlie positive train control, in terms of train performance calculators, if we can integrate that fidelity of train performance modeling into our optimization problems, then we can compose a higher fidelity dispatching plan and dispatching analysis.
Okay, there's been a couple of questions. There's a similar question theme around these questions. In your optimization model, when you minimize your cost in terms of time, do you consider the priority of the train or the value of the goods it's training or it's carrying, or the type of train, is that weighted into your objective function, your optimization model?
In the work or in the in the context where we have applied these methods, we do not use a priority weighted train runtime or anything beyond just a total train runtime calculation. But it is, if you, any linear combination of train variables and train parameters is a valid objective function for optimal dispatching, as well as for more complex optimization solvers. You can use nonlinear equations, but we use just this sort of total train runtime as a simplifying assumption, but it is extremely easy to add in train priority and begin to get closer to what the dispatcher is actually optimizing, let's say, in his or her head. They are considering factors like that. So, were this to be implemented in a real context on a real railroad, that level of fidelity would absolutely be necessary to get accurate results and really get much closer to what the dispatcher is considering. So in short, it's easy to incorporate that enhancement, but we don't just as a simplifying assumption that we make.
I guess a related question, and I think maybe someone answered this, is ability to consider, for example, a crew that's running out of hours. I know this was a very, very big issue, and some of your ETA work was on the cost of recrewing trains and predicting recrews. And is that factored into this? It sounds like that may be something that would be an additional add-in.
Right. Yeah, that is an additional that would be added into this problem as an additional constraint. And again, that is one where dispatchers are acutely aware of train of the clock for train crews. But just for some nuanced data reasons, it's not very easy to incorporate into the constraints in this context. Train crew timesheets are a little bit of a disjoint data set from some of the more dispatch oriented data. But completing that data fusion accurately and including train crew time as a constraint, necessary enhancement to get this closer to what a dispatcher really is considering in real time.
Okay. Number of questions here. One of them is you're optimizing for a minimum runtime. I guess, could you potentially optimize for maximum predictability of the future schedule, or sort of maximum likelihood of achieving that future optimal train plan? I just comment on the ability to structure your problem in that manner.
Yeah, and that is a common thread amongst amongst a lot of the optimal dispatch work. It's not necessarily what is the minimum that you could run to, but what is a realistic lower bound on what your trains can actually achieve. That gets to questions of how hard do dispatchers assume that engineers are going to push the trains, and how much of train performance do we want to try to squeeze out, and how much do we want to sort of lean off the accelerator and accept that more consistently, or a more consistently moving network is more efficient. That is again something that we would want to include in the optimal dispatch problem if you can quantify such a thing. The difficulty is really getting what's in the dispatcher's head, or what's in the railroad's desired operating strategy, and encoding that in math. So that's why some of this is some of these data-driven methods, they require a lot of domain expertise and a lot of talking to the people on the ground actually implementing these things. So it is able to be incorporated in here. Potentially in the data-driven sense, there may be some some useful information that can be gleaned from just looking at the data and assessing how conservative do we run the railroad relative to sort of optimal train performance or theoretical train performance. how conservative are we with pushing things.
Okay, a few more questions here. Thinking about like the effectiveness of your algorithm and more of a severe disruption, maybe like a weather or a more severe disruption to the line, and does it consider constraints such as yard effects, the number of trains you can have in and out of a terminal during a given amount of time, and just sort of questions on your comments on that?
Yeah, I think Tyler, you probably also remember some of this. We talked about some of these challenging problems about yard effects and sort of the composition of the network topology in some previous projects. It is not an easy problem to run or to consider every single variable on the network because these things are so interdependent. The line I'm showing here, the Essendon North, this relies on two other junction points, Nashville and Birmingham, both of which are large interchange points, both of which have a lot of additional traffic running through them. And it's absolutely true that there is activity happening in both those places that is impacting operations of trains out on the main line. So incorporating those factors is impactful but extraordinarily difficult, and so we would have to make you sort of wouldn't be able to compose the entire thing as an optimization problem, because scaling just kills you in this case, because what's happening in Nashville depends on what's happening on the other main lines that feed into it, which depend on the other cities and the other junction points at the end of those lines. So because everything is connected, it's tough to sort of draw the problem boundary. So incorporating some intelligence about what's going on in the yards and in the terminal points is necessary to fully understand how your main line is going to run. But that's that I would classify as an area of future work, composing the larger problem and considering those network effects.
Okay. One of the questions here related in you're basing this off of empirical data, so you have a very firm picture of what the future trains that are coming into your territory window look like. In reality, dispatcher, those trains may appear somewhat randomly in the future. So thinking about how much you incorporate sort of randomness in that future train arrival pattern into your optimization model, or is that something that you've thought about or considered?
Yeah, I think there is a degree of randomness to things, but if we're talking about the points at which additional trains are going to come on the network and the dispatcher is going to have to deal with those, that goes back to your prior question about what's going on in the yards, what's going on beyond the yards on the other main lines, what kind of traffic is crossing through Nashville or Birmingham in this case, and is going to impact the subdivision. And some of that, does have a degree of randomness and uncertainty when it's coming through the yards, but at other points, it's fairly predictable what's going to be coming off the main line and just passing through onto a given subdivision. So yes, I think sort of going off the previous answer, those are the known quantities and the things that we can quantify, such as scheduled traffic and sort of imminently arriving traffic. That's fairly easy to incorporate into consideration of dispatching on a single subdivision. But when you start talking about expectation and stochasticity, that adds a new dimension to your optimization problem, to any optimization problem.
Definitely. So a couple questions here about maybe some of your experience talking to the dispatchers. A good train dispatcher has to do a lot of this replanning in their head. I mean, how good is a human dispatcher relative to some of the the computer algorithms when it comes to doing this replanning on the fly, just based upon your experience and conversations?
I would say that the situation varies quite widely. A lot of my experience has been talking to dispatchers of single track territory, and busy single track territory at that. And in those cases, the degree to which human decisions diverge from computer guided decisions is quite a bit higher than the extent to which those decisions diverge in double track territory, or on subdivisions or lines in which capacity is not, or we're not running near capacity. So yeah, I think you will hear a lot of different answers to that question, but it is a good one. And there's a reason that we focused on single track territory for these sort of methods, looking at how the schedule diverges, and elements of unpredictability, because the degree of unpredictability is quite a bit higher in these cases. These methods certainly would be applicable to double track territory, or more consistently running main lines, perhaps out west. But I think you would find that the dispatchers there follow the computer and override those decisions much less frequently, and there are fewer questions about what went wrong or how we could improve performance.
Okay, I think just the interest of time here, we still got a number of questions. I'm going to pick two of them out of here, then we'll collect the rest of the questions and send them to you directly with the askers, and you can potentially follow up with them about that. So the two questions I have, the first one is there potential to use your methods to look at changes to the infrastructure or operations, such as runtime speed, to improve the dispatch solution? Maybe it's an infrastructure planning tool or investment planning tool. Is that something that this could be adapted to?
Absolutely. And the idea of taking empirical data plus optimization, and looking at what, sort of taking your baseline performance in your current infrastructure case, and then changing the infrastructure and sort of re-simulating that through optimization, just as you would do through RTC or another methodology. That definitely gives you the ability to assess what the impact of that additional infrastructure would be. But I think taking it one step further, not only can we assess what that impact would be, but we have the potential to actually optimize for things like what is the optimal location of a siding, or which are the optimal sidings to extend in length. And if we're not running sort of that global optimization problem, we could certainly look at where are our bottlenecks on the railroad. Where do the results of dispatch analysis indicate that we're having lots of issues, and where are trains getting congested and experiencing delays, and are those areas we can look at more closely in terms of infrastructure investment. So in short, yes, all of these data-driven methods, the incorporation of historical data with the ability to look at alternative scenarios, is very potentially impactful for those large and costly infrastructure decisions.
Okay, a final question, it relates to another application of this, is could you use this model as the basis for a fragility score, so to speak, of the train plan? Looking at different train plans and how quickly they fall apart given certain deviations from the plan to the actual runtime observed, and use that as a tool for that. That may help a railroad set up a better sort of train departure plan over a given subdivision.
Yeah, absolutely. This, as it was described in the question, that the fragility measure is fairly well studied in the literature, and robustness of planning and scheduling is a very high priority for the reasons that you outlined. And and so, without stepping on the toes of that work that is, very good in the theoretical optimization sense, I think I'll just add that, by incorporating historical empirical data with those methods to evaluate our plans for their robustness, because we have that additional intelligence, we can say not just what is sort of the worst case scenario of something breaking the plan, or what's the easiest thing to go wrong, but what's the easiest and most likely, because we have basically a large data set of what things actually happened, and what which deviations actually occur, and which deviations are just purely hypothetical, but we never really see out there in the real world.
Okay, well, thank you, Will, for the excellent presentation, and thanks everyone for the great questions. We'll collect the unanswered questions here and forward them on to Will and follow up. So thank you again, Will, for an excellent seminar, very interesting, a great presentation, and thanks to everyone for attending. Just a reminder that we do have additional seminars coming up during the remainder of the semester. I believe our next one is scheduled for Friday, March 19th, and we'll have Mike Roney, formerly of the Canadian Pacific Railway, talking about Heavy Haul 4.0, the future of heavy haul railroading. So thank you again for everyone attending, and we hope to see you again on a future Hay seminar here from the University of Illinois. Thank you.